Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 15, Part 2, Latin squares design. So we use the Latin squares design when we want to control for two confounding variables. So essentially, we want to look to block for two different confounding variables. Okay, so essentially this looks similar to a Sudoku puzzle, right? Where the rows and the columns all have to have the T treatments. So we have T rows and T columns, and the T treatments are randomly assigned such that the rows and columns, that treatment appears in every row and every column exactly once. All right, what are the advantages? We can compare T treatment means in the presence of two extraneous sources of variability. The analysis is fairly simple. The disadvantages is that the number of treatments has to be slightly small, between 5 and 10 treatments is best. The error term might be slightly inflated, so it might be difficult to detect the differences among the treatment means, and the effect of each of the treatment on the response must be approximately the same across the rows and columns in order for this design to be valid. All right, so suppose we have two different variables, and we're going to have T different groups in the rows and T different groups in the columns. Essentially, we're going to have for variable 1, T1 through T sub T. But then the second row is going to start at T2, go all the way up to T sub T, and then go to T1. And so this is guaranteeing us that we only have each of the treatments once for every row and column. All right, the row means are going to be your y bar I dot dots. And your column means are your y bar dot j dots, okay? Your treatment means are your y bar dot dot k's, okay? So we have y bar dot dot 1 all the way down to y bar dot dot t. Okay, let's look at an example because sometimes I find this to be a little more straightforward. So suppose we have 4 drivers and 4 cars. Okay, so we want to look at the reduction of automobile emissions. Our response is the reduction in nitrous oxide. Our treatment is the 4 gasoline additives, A through D. Our blocking variable is cars, because we know that different cars could have effects on the mobile emissions. And then the way people drive could also have an effect on mobile emissions. So we're going to compare 4 cars, 4 drivers, and look at the differences in the gasoline additives while blocking for the car and the driver. So here you notice that we are going to randomly assign the treatments such that if we look here in the column, we have A, B, C, and D. And in the row, we also have A, B, C, and D, okay? And that's true for every row and every column. Each of the treatments shows up exactly once, okay? So we will get back to all of the pieces, but I just wanted to show you an example so that it would be more concrete as to how things are produced for this model. All right. The actual model is written out by Yijk, where we have mu plus tau k plus beta I plus gamma j plus epsilon ijk. So the Yijk is our response variable for the ith row and the jth column receiving treatment k. Mu is the overall mean, an unknown constant. Tau k is the effect due to treatment k, an unknown constant. Beta I is the blocking effect due to row I. And gamma J is the blocking effect due to, this should actually say column J. Apologize for the typo. That's an unknown constant. And then we have epsilon ijk, which is the random error associated with the response from an experimental unit, or if we're talking about people, the subject, in row I and column J. And I'm going to just say receiving treatment K. All right, remember those epsilon ijk's follow a normal distribution with a mean 0 and a variance sigma squared epsilon. Those epsilon ijk's are independent. And so when we think about our yijk, since the model is completely additive, there's no interaction terms, we know that it also follows a normal distribution where the mean is equal to mu plus tau k plus beta I plus gamma j, and the variance is equal to sigma squared epsilon. All right, the main interest here is really the treatment, but we're just controlling for the effect of the row variables and the effect of the column variables. All right, just like before, we could think about the expected value of yijk is equal to the expected value of mu plus tau k plus beta I plus gamma j plus epsilon ijk. And since this is a linear combination, we can just pull the expected value through. That's the expected value of mu plus the expected value of tau k plus the expected value of beta I plus the expected value of gamma j plus the expected value of epsilon ijk. All right, since mu is an unknown constant, the expected value of mu should just be mu plus tau k plus beta I plus gamma j. And then this should be plus 0 because the expected value of those epsilon ijk's are 0. So overall, we get the expected value of yijk is just mu plus tau k plus beta I plus gamma j. And then we can find the variance in a similar manner of yijk. Well, essentially, that's just the variance by substitution, mu plus tau k plus beta I plus gamma j plus epsilon ijk. And once again, that's a linear combination. So we get the variance of mu plus the variance of tau k plus the variance of beta I plus the variance of gamma j plus the variance of epsilon ijk. Now there's no, the mu's, the taus, the betas, and the gammas are all independent of the epsilon ijk's, so there's no covariances to worry about. And what happens here is that since mu, tau k, beta I, and gamma j are all unknown constants, they shouldn't vary and their variance should be 0. So we're just left with the variance of epsilon ijk, and the variance of epsilon ijk is sigma squared epsilon. And so we also get that the variance of yijk should also equal sigma squared epsilon. All right, so this is our setup for the Latin squares design. There's a lot of notation to think about. We're gonna just look at one more set of notation. Okay, so yijk is the observation of the ith row, the jth column receiving treatment k. Y bar I dot dot is the sample mean for block I. All right, Y bar dot J dot is the sample mean for block J. The Y bar dot dot K is the sample mean for treatment K. The Y bar dot 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 is our overall sample mean. And if you want, really, you can either use the notation in column 1 here, right? Or if you wanted to, you could use a second notation where you just said you're going to kind of ignore that last piece and just say, okay, Yij is the observation in the ith row and jth column. Y bar I dot is the sample mean for block I. I'm going to stick with this left side for now, but really either one should give you the same information. But I just wanted to note that depending on what notation you're looking at for Latin squares design, you could see it in either fashion depending on the textbook that you were looking at.